Sorry. So hi, I'm Jason Ross. I'm here at the NASA Institute for Advanced Concepts Fall Symposium in Hampton, Virginia. I'm here with Professor John Slough, who's just made a presentation what his firm MSNW has put together for a fusion-powered rocket, citing the ability to get to Mars, for example, much quicker without exposing astronauts to the hazards of space and other equipment. I was hoping you could just share with our viewers a general idea of what your idea is with your fusion rocket.
Well, yeah, so we've perceived that the problem with why we're not on Mars now is that it costs too much and it takes too long. So the way that those two problems can only be addressed is if we manage to have a rocket where the ratio of the mass of the rocket to the power it delivers is very small. And at the same time, the exhaust velocity must be much higher than what you can achieve with chemical energy in order to shorten the trip time. So both of those are required to reduce the amount of material that you need to bring into space and the time it takes to get there. So there's probably only one energy source that has that kind of energy density, if you want to call it, and that is nuclear. And now nuclear fission has been proffered for space transportation, but there they can only use the thermal energy that's derived from the fission due to the nature of the reactants itself. Fusion's always held the promise of being able to generate particles at very high energies, and that they could then use these particles to have a very large exhaust velocity. What we've decided was that the fusion process itself can create a tremendous amount of energy, and that if it were surrounded by a different propellant other than the fusion plasma itself, that we could then transfer that energy to that material and then achieve both the high velocity that we need for rapid transportation and reduce the mass cost, because we actually use the propellant to compress the plasma diffusion conditions. So we kind of do dual duty there. So we don't. So the energy that's released by the fusion event goes directly into propulsive motion rather than passing through some kind of an energy conversion system, such as a boiling water reactor or whatever, boiling lithium reactor or whatever you might imagine for space. So it's a very simple system. It is really kind of based on nuclear devices that were developed in the 50s for much different purposes. But the challenge was to not have high yields like you would see in a hydrogen bomb, but to bring that down to a scale that essentially that energy could be created and transferred to the rocket ship without damage to the rocket ship. And we believe that we can do that for two reasons. One, we reduce the energy by about a factor of 1 billion over a hydrogen bomb. That's still, given that you may not even think that's quite enough, but actually it is. The other thing that's very important about the way we proceed to make the fusion event is we use a magnetic field to induce this lithium is the preferred material to as the shell that implodes our plasma and creates the fusion conditions. We use magnetic fields to do that. And the good part of that is that after we've created this large burst of fusion energy and transferred it to the lithium propellant becomes an ionized gas itself. And the magnetic field then guides it out the end so that it can't re-strike against the rocket surface. All chemical rockets depend on the wall transmitting the impulse in the nozzle to exit in a specific direction. So here we avoid the energy transfer to the rocket, we protect the rocket, all done at the same time. So all these things coming together means that we can now have a rocket ship mass that is, compared to the power produced, a very small number. So we don't spend much mass in producing the energy. So that's sort of the basis behind the fusion-driven rocket.
Okay. Let me ask you, in regards to the fusion process itself,
Yes.
your plan uses DT fusion.
That's right.
Let me say, there's some talk about using helium-3 as a potential source for aneutronic fusion reactions. What are your thoughts on that in space and here on Earth?
One thing we found, and this has always been sort of a bias against fusion using DT. It's obviously the easiest and most energy productive way to create fusion energy. The DT reaction has the largest cross-section at the lowest plasma temperature. So it's what I call the low-hanging fruit of all the fusion reactions. And all conceptual designs for Earth-based reactors are always based on DT for that reason. Now, helium-3 would be an interesting alternative propellant, but the problem there is it doesn't exist naturally. It's only produced by the decay of tritium, which is something that makes it, and tritium itself is also only produced by reactions, man-made reactions. But the process that's required for making it aneutronic would yield it's much more difficult fuel to actually convert into fusion energy. But the real problem that I see is having neutrons is only a problem in an Earth-based reactor, and that you need to shield it. In space, all but the small direction that the spacecraft takes in terms of the solid angle, the neutrons just fly off into space harmlessly. So neutrons aren't bad. Neutrons are actually good in that they're volumetrically absorbed, meaning that when we try to heat our propellant, in this case the imploding shell that surrounds our plasma, and to bring it to the fusion condition, the whole body of that absorbs it, and so we can heat the entire mass and that way convert it all into an ionized gas. So if it were trapped in the form of particles, the particles themselves would be retained in the plasma, and then you have the problem of how do you get the heat out. So maybe for a terrestrial reactor it might have some benefit. I'm not sure about that either.
Okay.
So neutrons are good as far as I'm concerned.
Okay. They're overly maligned, huh?
Yes, that's right. Well, they obviously are can modify and transform materials, and that is good because that means you can create the fuel that you need, the tritium fuel from the reaction itself. The other reason people fear neutrons is that it is the means by which a chain reaction occurs in a fission reactor. So, I think it's got its bad reputation from fission, but not so much from fusion. Okay. And so we'll see. But transforming materials could be another application.
Okay.
Such as waste from fission reactors.
Right. Let me ask you, your proposed design uses a pulse propulsion technique similar to the, say, the Orion project studied earlier in the U.S. What could you say about Orion as inspiration, or about international work on nuclear rockets of this sort? So
it's true. Orion was, there's a lot of time and energy spent in trying to understand how to use nuclear energy in a way that they knew would produce the kind of copious amounts of energy required for space travel. And the Orion project, unfortunately, at that time was too close to the concept of an atomic bomb to find any widespread acceptance. In fact, it was banned by all countries. But the main problem with fission is that in order to get enough fissile material together to have a chain reaction that will produce these sort of energies requires a very large amount of mass, and therefore a very high amount of energy release. So the amount of energy released couldn't be reduced by 1 billion the way we'd like to do with the fusion reaction. Fusion reaction can really occur at any scale, and that means it's scalable down to a level that we can use it. So the only successful demonstration of fusion has been with a pulse system. So we felt like it's got good, a firm grounding there in the fact that at least there are several countries that know the process. Right. Now, this is slightly different in that we intend to use a magnetic field to confine it, and that allows us to technologically to make it much simpler. So there have been studies done in terms of this implosion technique that we intend to do with magnetic fields in other countries, and particularly back in the Cold War days. So a lot of that information, I think, is now lost because of the retirement and death of the Soviet physicists, but also just simply these things were not written down. And so, but there's a great body of knowledge worldwide on how to maybe do this. So I think if we can have a demonstration of its potential through a successful implosion, which we can do in our laboratory, that we'd probably find worldwide interest increase in this process. Because you could also, needless to say, use it for terrestrial energy generation.
Right. Okay, let me ask you one last thing then. Sometimes these projects are discussed as whether it's a question of the scientific feasibility versus the political will, which means funding.
That's right.
Those might not actually be different questions, since scientific breakthroughs occur when you have funding. What do you think about the political climate of all this?
So I think we were under the radar right now as regard to what we can demonstrate. So I think that we have fortunately, from other fusion experiments that I've conducted in the past, a large amount of equipment that we can apply to this particular task. So that allows us to actually get much further along in this process. We were even thinking it was close to that we might be able to achieve break-even, which is something that hasn't occurred yet in controlled nuclear fusion, even with a simple experiment conducted by very few people in this manner. So that part of it is fortunate for us that we can achieve that. But obviously, future development, and particularly with the sophistication and the reprating and all the other aspects of space travel, will require significant investment by NASA. But we hope we can, interest the world with the fact that fusion isn't always 40 years away and doesn't always cost $2 billion.
Okay. Great. Thanks a lot. Mm-hmm.